Hello students, in lecture 8 of your course Elements of Discrete Mathematics, here first we shall discuss the certain illustrative examples, the definition of Boolean subalgebra, examples related to subalgebra, then the definition of isomorphic Boolean algebras, and the definition of Boolean polynomial. So first we consider an illustrative example here where we have to show or we have to prove, example 1, prove that no Boolean algebra can have three distinct elements. So in this case, how we shall prove? We will consider a Boolean algebra that have three distinct elements, and by proceeding further, we will get some contradictory statement, and due to that we will say that our consideration or our assumption is wrong, and this will be the process here. So here first we are considering a Boolean algebra B having three elements. Let B must have then B must have at least two distinct elements, 0 and 1, as identities for operations for plus and dot respectively. Let A be the third element of B. Obviously, we have already discussed that a Boolean algebra must have at least two elements. So here we want to show that a Boolean algebra cannot have exactly three distinct elements. And here we are considering that B has three distinct elements. So obviously two distinct elements are 0 and 1. These must be there in every Boolean algebra, and then we consider that A be the third element of B. A be the third element of B. Since B is a Boolean algebra, so a complement of every element must exist. So suppose if A is the distinct third element, then its complement A dash must belong to B. And by complement law, you can say A plus A complement is 1 and A dot A complement is 0. This is our complement law. So now three situations arises. Number 1, either A dash A complement will be equal to A, or A complement will be equal to 0, or A complement will be equal to 1. Why these three situations arise? Because we are saying that the Boolean algebra we have considered, it has three elements. Out of those three elements, one is 0 and one is unity here, and third element is A. And you know the complement of 0 is 1 and complement of 1 is 0. Now we have considered here third distinct element A, and if we talk about the complement of A and it belongs to B, then definitely this A complement will be either equal to 1 or will be equal to 0 or will be equal to A. So these are the three situations here, and we will be considering each of the case separately. Suppose case 1, suppose A complement equal to A, then what will happen? Then by complement law we can write A plus A complement is 1. You can see this is true from complement law. But according to our given condition in case 1, that A complement is equal to A. That means you can put here A. A plus A is 1. But A plus A is equal to 1, equal to A. How is that? This is due to idempotent law. We have explained in the earlier lecture, means lecture number 7, that A plus A is equal to A, and due to this idempotent law, this A plus A can be written as A. So you can say A equal to 1. but you have considered that this a is distinct from 0 and 1, and here you are getting that a equal to 1, and a dash a complement is also 0, then a dot a is 0, that means a equal to 0. So if we assume this situation that a complement is equal to a, then we are getting that either a will be equal to 1 or a will be equal to 0. But we have already assumed that this a, because if we are saying that the Boolean algebra B having the three distinct elements, then definitely this a neither will be equal to 1 or nor will be equal to 0. So that is a wrong statement here, or the wrong expression we are getting, that a equal to 1 or a equal to 0. So therefore, a complement equal to a, what we have assumed in the case 1, is not possible. This is not possible at all. So let's move on to case 2. When you are saying that a complement is equal to 0. In case 2, when a complement equal to 0, then a plus a complement equal to 1 by complement law. So because a complement you are assuming that 0, so you get a equal to 1. But it is again not possible. So the choice a complement equal to 0 is not possible. Now we are assuming the third case, when a complement is equal to 1. Then by the complement law again, a dot a complement equal to 0. That implies, because a complement is 1, so a dot 1 is 0, a dot 1 is a, so that is equal to 0. So again, a wrong choice, because we are saying that a is not equal to 0 and not equal to 1. Therefore, a Boolean algebra cannot have three distinct elements, and that was the question we wanted to prove here, that prove no Boolean algebra can have three distinct elements. So this is about first illustrative example. Now the second illustrative example here. In fact, such kind of expressions, in a Boolean algebra, we have to show this a plus b. In fact, if nothing is mentioned here, then it is automatically it should be automatically assumed that here is the dot operation. Similarly, in between a and b there is the dot operation, and here dot operation. So dot operation, we are not writing it further in the simplification of this expression. Here we want to show that this left hand side of expression is equal to right hand side of the expression. So such expressions are called the Boolean polynomials. Such expressions are called, if simply I'm writing this left hand side, then this is a Boolean polynomial, and this right hand side is also a Boolean polynomial. In fact, because here these elements, these are the variables, in fact they belongs to the Boolean algebra, and the expression in terms of a, b and c, like that becomes a Boolean polynomial. So in this example, we want to prove that left hand side is equal to right hand side. So in such problems, what we should do, uh, we should consider either left hand side or right hand side. If we are considering the left hand side, then we should arrive at the right hand side by using all the axioms of Boolean algebra. These are the four axioms: the uh, commutative law, identity law, distributive law, and complement law. These are the essential axioms of the Boolean algebra, and other properties are the idempotent law. Uh, other properties are, this is identity law here. Other properties are idempotent law, then the boundness law. These are the most important properties. The absorption law, etc., which we have mentioned in the last lecture 7. So in view of these properties, we can simplify the expression. So here we are considering that left hand side is this a plus b. In fact, nothing is mentioned here, then in fact it is dot here, dot here. So a plus b dot b plus c dot c plus a. So when we simplify this, a plus b is kept here, and using the associative law we can keep these two in one bracket. Now by commutative law we can write this b plus c as c plus b, and this we are keeping as such. Now you can see here this is in fact c plus this operation c plus, and here c plus, and here is dot. So by the distributive law, in fact, these two factors collectively can be written as c plus b dot a. In fact, dot is here, and I can elaborate it in this way that if we are having c plus b dot a, in fact, this is the situation that this is b dot a. Now, by the distributive property, this c plus can be distributed with b and with a. So that way you can write it as c plus b, because we are distributing this with b, and dot here c plus a. So due to this fact, this expression c plus b dot c plus a can be written like this. So now here again here is dot. So now we can distribute this dot operation. Now again we will apply the distributive property. Now earlier we have distributed this plus over dot. Now we are distributing this dot over plus. So what we get, the whole thing will come with c, and the whole thing will come with this ba. So consequently what do we get? A plus b dot c. In fact this no, actually, it is being given in such a way that we are distributing this side with a. That means a dot c plus ba, and similarly this part as with b dot c plus a, c plus this part. So in fact we are getting this kind of expression. Now you again apply the distributive law, because here again a dot. So you, when a dot is there, then you will take it here, a dot c. Again you will take it here, a b a. In fact a dot b dot a. So b is here, b dot c, and plus b dot b a. So now ac plus, by using the commutative property you can shift this a on this side, aab plus bc, and this is bb. Now by the idempotent property, a dot a and b dot b, in fact it is a only, and this b dot b is b only. So we are getting ac plus ab plus bc plus ba. So now this ba, using the commutative property, can be written as ab. This can be written as ab. So in fact it becomes ab plus ab. So again this is the one element and this is the one element. When we are adding two elements of the Boolean algebra, we get the one element itself due to the idempotent law. And this is AC plus BC plus AB. So now we are getting AB plus BC. In fact, this is AB, we are writing it here, then BC, and AC by using the commutative property can be written as AC. So in this way, we have obtained the right hand side. So always keep in your mind while you solve these type of problem in exam, then you should mention the respective property which you are using at a particular step, as are given in the right hand side of this part, this question here. So that is it about this example. Then the next topic is the Boolean subalgebra. So what is a Boolean subalgebra? So obviously we are talking about subalgebra, so obviously there should be a Boolean algebra first, and then this Boolean algebra we will look for a subalgebra. So definition is, let B plus dot complement 0 1. This is identity with respect to plus operation and identity with respect to dot operation. Be a Boolean algebra. The whole structure, this whole structure is a Boolean algebra. A non-empty subset S of B is said to be a subalgebra or a sub-Boolean algebra if S itself is a Boolean algebra with respect to these operations plus, dot, and complement of B. So this is the definition of subalgebra, or you can visualize the situation in this manner, that if B is the Boolean algebra with respect to the operations plus, dot, and complement, and the elements, identity elements 0 and 1 are there, and if we are having a subset of if this subset with respect to these operations also satisfies the properties of Boolean algebra, then you can say that this S is a subalgebra of this Boolean algebra. For numerical point of view, what you can do, you can keep in mind this theorem 1. It states that a non-empty subset S of a Boolean algebra B is subalgebra of B if and only if S is closed under three operations of B, that is plus operation, dot operation, and complement operation. So just understand the meaning of this. What is the meaning of this statement that S is closed under these three operations? It means that if you take A, B, two element from S, then A plus B also belongs to S, A dot B also belongs to S, and A complement also belongs to S. In place of A, you can write the B complement also belongs to S. That means it simply means that for every element of S, its complement also belongs to S. So meaning of writing this situation mathematically is same as we are saying that S is closed under the three operations of B plus, dot, and complement. If we are writing this, that means S is closed with respect to this plus operation, means you take any two element of S and you apply the plus operation, the new element will again be in S. Similarly, if we are writing here that A dot B belong to S for all AB belongs to S, means this S is closed under the dot operation, and if complement of each element belong to S, then you can say that S is closed under this complement operation. So now we can have one example of subalgebra. So you know this, if we consider a subset S phi ABC of the Boolean algebra B, which is in fact the power set of the set X. Suppose I'm taking this X is having the elements A, B, and C, then you know that for this set a power set is in fact B. Power set will consist 8 elements here, so this is in fact power set. And in our earlier lectures we have proved that this power set of any set forms a Boolean algebra with respect to the three operations, that one is union, intersection, and complementation. So union and intersection are the binary operations on this power set, and complement is the unary operation. So with respect to these three operations, this B forms a Boolean algebra. And in this B, you know that in fact the identity with respect to union is phi, and identity with respect to intersection is in fact this is with respect to union this is phi, and with respect to intersection the whole set itself, means the set X itself. So actually this B is a Boolean algebra. Now we want to show that S is a subalgebra. So either we check all the properties or simply check these three, properties. So how we can check these three properties? Let us see. Here we should check this plus law. In fact, in place of plus here we will use union, and in place of dot we will use intersection, and complement is as usual. So union means you will check whether with this set S is closed with respect to union or not, means the union of two elements of S is in S itself or not. So that can be checked with the help of a composition table. Suppose you write here phi A, then BC, and ABC. Here we are having ABC, and similarly phi A, BC, and ABC, suppose. So now you prepare this table. Phi union phi is phi union A is A, and here is BC, and similarly ABC. Now here again, if you take union of A with phi, then here we'll have singleton A with A singleton A. It becomes A, B, and C, etc. So in this way, if you construct this composition table, you will observe that all elements in this table are elements of S itself. Similarly, when you construct the table with respect to intersection, here, then you will observe that in this table all elements will be from S. And similarly, when you construct the table with respect to complement, for example, complement of phi is X and complement of A is BC, etc. So in this table you will also observe that the complement belong to the same set itself. So that way this S is closed under the operation union, intersection, and complement. Therefore, this S is a Boolean subalgebra of the Boolean algebra B. Now let's look at example 2. Consider the Boolean algebra. This we have also discussed in the earlier lecture, that this forms a Boolean algebra. But for this, in place of plus, if we say that A plus B, in fact the operation is LCM of AB. And if we write A dot B, the operation is in fact GCD of AB. So in this way, and complement, in this case is 70 by A. So using these three operations, if we check, this is a Boolean algebra. And in this, if we are taking this element of four, this set of four elements, then it forms a subalgebra. By the same logic or by the same procedure as done in this example 1, you can check this example 2, that here S also forms a Boolean subalgebra. Next one, theorem. If S is a Boolean algebra, if S1 and S2 are two subalgebras of a Boolean algebra B, and S1 intersection S2 is also a subalgebra of B, then this S1 intersection S2 is also a subalgebra of B. So in fact here, for a given Boolean algebra B, we are given two subalgebras S1 and S2. And we have to show that the intersection of these two subalgebras, is also a subalgebra of B. So here we can proceed in the way what is given in the theorem number 1. Let S1 and S2 be any two subalgebras of Boolean algebra B. We show that S1 intersection S2 is closed. This is according to theorem 1 with respect to the operations plus, dot, and complement. So although in view of theorem 1, we need to show only for plus and complement. Clearly S1 intersection S2 is non-empty because 0 and 1 are always there. Because if we want to choose two elements, then first of all we have to show that this particular set is non-empty. Obviously, because S1 always have 0 and 1 and S2 also have 0 and 1, that is why their intersection will also have 0 and 1 element. Now you take any two element from S1 intersection S2, then you can see AB belongs to S1 intersection S2. So AB both belong to S1 and as well as from S2. But you know S1 is a subalgebra, therefore A plus B belongs to S1, A dot B belongs to S1, and A complement belongs to S1. Similarly, A dot B, when you say that A, B belongs to S2 and S2 is a subalgebra, we can say that A plus B belongs to S2, A dot B belongs to S2, A complement belongs to S2. So using these two situations here, you can see this one and this earlier one here, we were saying that these are belonging to S1. So using these two situations, you can see A plus B is belonging to S1 as well as to S2 here, as well as to S2 here. Similarly, A dot B is belonging to both S1 and S2, and A complement is also belonging to S1, S2. So using these two, you can say that A plus B belongs to S1 intersection S2, A dot B belongs to S1 intersection S2, A complement belongs to S1 intersection S2. Hence, you can say that S1 intersection S2 is a subalgebra of B. Now, here, one question can be looked into, that is, if S1 and S2 are subalgebras of a Boolean algebra of a Boolean algebra B, then what you can say about the intersection? Is it subalgebra? Not intersection but union. Is it subalgebra of B or not? So this is a question. You can try this. Next come to the isomorphic Boolean algebras. So if we have two Boolean algebras B and B dash, then B and B dash are said to be isomorphic if there exists a 1-1 and onto mapping F from B to B dash such that these three properties are satisfied. What are the properties? That F of A plus B is equal to F of A plus F of B, F of A dot B is equal to FA dot FB, and F A complement is equal to F of A then complement of whole. So the definition is given in a very simplistic situation, that in this B, Boolean algebra B, the operations are plus, dot, and complement, and obviously when the same operations we are considering, then the 0 element and 1 element is there. Similarly, this B dash is also having the similar type of configuration, B plus dot complement 0 and 1. So in this idealistic situation, the definition is given over here that these B and B dash will be isomorphic. But what happens if there is some different situation? That it may be the situation that here we have the operation plus, dot, complement 0 and 1. And in place of B dash, if we think about the structure of the power set, the structure of power set, in fact, in that situation, we will be having that in place of plus, we use union, we use then intersection in place of dot, and complement is complement in some sense here, and in place of this we have phi, and in place of this we have x. So now this is also a Boolean algebra and this is also a Boolean algebra. These two can also be isomorphic. So in that situation, how we should write these three properties? In that situation, the properties will be written in this way, because you are defining the function from B to B dash. So here the elements are in this case elements are maybe some numbers, and here elements are some you can say sets. So if you want to define a 1 1 and onto mapping, then for every element here there must be one element here. For every element here there must be element some there. So this kind of 1 1 and onto mapping you have to define so that these properties are satisfied. So in right in this the b dash, operations are not plus and dot. So therefore the first property in this situation will be written like that: f of a plus b is equal to f of a, because if you are writing a here, the element f of a will be the part of b dash, and if you are writing b here, this element will be part of fb will be part of b dash. Now if we apply the operation plus between a and b, but in the elements in b dash, the operation plus have some different meaning, because in place of plus we are using union, so it should be defined like this. Exactly in the same manner you will write f of this a dot b will be equal to f of a, because in place of dot in right hand side Boolean algebra we are having intersection, so we write f of a intersection f of b, because if here element is a, then definitely here f of a meaning of f of a in fact is set. That is why we are using the operation union and intersection. And similarly, if f of a complement is there, then it will remain as such. But the meaning of complement in right hand side will be the complement of a set, and here the complement of a number in fact. So depending on the structures of the Boolean algebra, the definition these three properties can be modified in the same sense. For example, we have the same situation as I have discussed. In this example, you can see the Boolean algebra B of power set ABC and a Boolean algebra B dash. This one, this is the Boolean algebra of divisors of 70. Then B and B dash are isomorphic. In fact, we have a mapping B to B dash defined by, means you if you can define 1 1 onto map so that all the properties are satisfied, those three properties, then these can be the isomorphic Boolean algebras. So the mapping is defined here in this way, that the set B, this set B is having the elements 1, 2, 5, 7, 10, 14, 35 and 70, and here this set B is having the elements, this is basically the power set phi, then singleton A, singleton B, singleton C, singleton not then pairs AB, BC, CA, CA and ABC. So these are the eight elements. 1 2 3 4 5 6 7 8 elements are there. So this if we can define the 1 1 onto map. If 1 is associated with phi, then in fact here it is opposite. In fact, this had been considered as B and this as B dash. So in either way, because this is a 1 1 onto function, we can define the mapping in either way. So here we are defining in such a way that f of phi, here image of phi is 1, f of phi is 1, f of a is 2, f of the singleton B is 5, f of singleton C is 7, f of AB is 10, f of BC is in fact 35, f of AC is 14, this is 14, and f of ABC is in fact 70. So you can see corresponding to each element we have its image there in B dash. So this is the mapping f from b to b dash, which is 1 1 and on to. And you can also check in here that f of ab means in fact you will have f of a plus b means a union b will be equal to f of a plus f of b. And this is in fact because f of a is here inside b dash, and b dash is the set of these numbers, and set of these numbers, the meaning of plus is LCM of fa and fb. For example, if we are having this set and this set, then f of a means 2 and f of b means 5. So actually meaning is LCM of 2 and 5, that is 10. So in this sense we can similarly we can have f of a intersection b that must be equal to f of a dot f of b, that is equal to GCD of fa and fb. So we can we can check all the three properties. That means f of a complement also can be checked that it will be equal to this thing. So in this way you can check that these two Boolean algebras b and b dash are isomorphic. Lastly, we have the definition of a Boolean polynomial. First, we have the Boolean function. Boolean functional or this Boolean polynomial is an expression derived from finite number of applications of plus operation and the dot operation and complement operation to the elements of Boolean algebra. For example, the expression a dot b or a complement plus b complement, a complement plus b and complement of whole plus ab complement x plus ab. So this is one Boolean polynomial, this is another Boolean expression or polynomial, this is another. So these are the examples of Boolean functions. So in any Boolean algebra, we know that 2a equal to a plus a equal to a, 3a is this thing. And this way n into a equal to a. So n is any positive integer. Also a square equal to a. And when you write a cube can be written as a dot a dot a. So this a dot a gives you a. Then further a dot a gives you a only. So in general a raised to power k is a, where k is any positive integer. Thus in any Boolean polynomials you will not see any multiples or powers of the same elements. So this is the speciality of a Boolean polynomial. So more examples related to Boolean polynomial we can see, we'll see in the subsequent lectures. So that's it about this lecture. The content had been consulted from these books. Thank you.